Alright, so we're at 988 now, and we're drawing Lewis structures of these different chemicals. 988, ASCl4 plus. ASCl4 with a plus charge, alright? So we want to determine how many, I think we already did this one. Yeah. So we're on B, ASCl, let's see, 988 plus, ClO2 minus. ClO2 minus. On this one here, we have oxygen bringing 6 times 2 is 12. Each oxygen brings 6 valence electrons, and one chlorine brings 7 valence electrons. And then there's one extra valence electron because of that negative sign there. So there's 12, 19, 20 valence electrons. Chlorine is in the middle, oxygen's on the outside. We have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons here. Now there's 8 around chlorine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There we go. Now, the result of this is that we have a formal charge. We identify formal charge by looking at how many electrons, valence electrons it brought versus how many electrons are right directly around it. And these lone pairs, each one counts as an individual electron. So 1, 2, 3, 4, 5, 6, and this bond counts as 1 electron, 7. So it brought 6 and it has 7, so there's a -1 charge there, a -1 charge here. This one brought 7 and has 1, 2, 3, 4, 5, 6. So there's a +1 charge there. All right, so the minus charge is going to want to be on a more electronegative atom, which is the oxygen. But we can bring 2 of these electrons in here and form that, and then we'll have no charge here. So this is going to probably be the correct Lewis structure for 988. Although they show just the minus sign there, right? So here we have 1, 2, 3, 4, 5, 6, 7. So I would say that is the correct Lewis structure for that one. All right, 988C, HNO2. Okay. HNO2. Now, we have to identify what the central atom is. Well, hydrogen can't ever be a central atom, so we know it's going to be nitrogen. And the question is, where does that hydrogen, where is it coming off of? Is it coming off of the nitrogen? And the answer is no, because this is an acid. It's nitrous acid, and it's an oxy acid. And oxy acids, the protons, the H's, the hydrogen ions that are given off, always come off of the oxygens. So we know that the oxygens are around the nitrogen, and that off of one of these oxygens we have our hydrogen coming off, okay? So we can add up how many valence electrons, 12 from oxygen, 5 from nitrogen, 1 from hydrogen, 12, 17, 18 altogether, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, so we didn't quite fill up this one here. We need 2 more here. We could make a double bond between these 2 and those 2 like that, if we wanted to. Let's just try that for now, just to see how we would work through such a thing. And now that would give this 8. Nitrogen has 8 electrons that it has access to. 2 here. Nitrogen has access to 2 here, 2 there, 2 here, and 2 there. So that's 2, 4, 6, 8. Oxygen, 2, 4, 6, 8. Hydrogen just wants the 2. This oxygen, 2, 4, 6, 8. All right? But now we have to look at formal charges and identify what the formal charges are. This oxygen has a formal charge of -1. It brought 6 electrons, and it has immediately around it 1, 2, 3, 4, 5, 6, and this bond counts as 1, 7. Nitrogen brought 5. It has 1, 2, 3, 4, 5, so it's fine. This oxygen brought 6. It has 1, 2, 3, 4, 5, so it has a +1 formal charge. So if we can identify a configuration that has no formal charges, it would be better. And so to get rid of this formal charge, we want to form a double. We could form a double bond with these electrons. But I'll redraw it down here so that you can see the change that we do. All right. If we want to reduce this -1 or remove the -1 formal charge, we can make this a double bond. Remove these electrons and make them a double bond. So basically bringing them in here. And now that'll have no formal charge. But now nitrogen has too many electrons. So we have to remove these electrons and put them onto here. and form that species there. So now this oxygen has no formal charge, this nitrogen has no formal charge, that oxygen has none, and then hydrogen has none. So that is the best Lewis structure. Okay, that's HNO2, 988 D, xenon difluoride, XEF2. XEF2, identifying how many valence electrons? 8 plus 14. Fluorine each brings 7. 22. Xenon is going to be our central atom, fluorine on each side. We need to have 1, 2, 3, 4. Now we have 1, 2, 3, 4, 5, 6, 7, 8 electrons around the central atom. So we have 22 minus 8. 20 minus 8 would be 12. 14 left over. Is that right? Yeah. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And everybody has 8 electrons, but we have, so we minus 12, we have 2 electrons left. So we can put them on our xenon. And we do that because they can't go on the fluorines. Xenon has extra space. It's in the 3rd column or lower, right? So you have to be in the 3rd column or lower. So you have to be either argon, krypton, or lower than the 3rd row or lower, to have D electrons and be able to have what's called an expanded octet. So you can actually have more than 8 electrons around it. All right, so that's 988. So that's the answer there. 988, 990. Draw Lewis structures for SiCl4. 7 times 4, 28 electrons brought by these chlorines. This is a 4 electrons. 32 electrons altogether. Silicon in the middle. Chlorine, 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 chlorine. Silicon already has its octet, so we have we've consumed 80 electrons. 8 times 4 is 32, so 8 times 3, so we have 24 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24. So there we go. That's our, we can look at formal charges. We'll see that all of them have no formal charge, right? All right, so PF3. Phosphorus in the middle. Fluorine, fluorine, fluorine. How many? Phosphorus brings 5. Fluorine 3 times 7 is 21. 26 valence electrons. 1, 2, 3, 4, 5, 6. First thing we do is fill up our middle. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 5, or 6. So that is going to be our Lewis structure for phosphorus trifluoride. I think I said phosphorus tetra, but it's phosphorus trifluoride, right? All right, so phosphorus hydride, pH3. All right, so phosphorus had a, our phosphorus brings 5 electrons. Each hydrogen brings 3, so there's a total of 8 here. Phosphorus, hydrogen, 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 and then we have to have 2 electrons there. And there's no formal charge. 1, 2, 3, 4, 5, 1, yeah. So that's that one. And then 1, 2, 3, 4, 5, 6, 7, 8 electrons consumed. All right. SCl2, SCl2. Okay. So 990 SCl2. 7 times 2, 14 electrons from chlorine, 6 electrons from sulfur, 20 electrons altogether. Sulfur, chlorine, chlorine. We have to fill the octet of the central atom first, and then we fill the octets of everything else. I didn't count. How many was that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20. Draw the Lewis structure for... Okay, yeah. Draw the Lewis structure for carbon disulfide and the cyanide ion. So this is 992 now. 992. carbon disulfide, CS2, and Cn ion, Cn minus, right? So carbon disulfide, carbon's always a central atom if it's given a choice. All right, so sulfur like this. Sulfur brings 2, 6, 12 plus 4, 12 plus 4, 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we see that we're not going to have enough electrons to completely fill the octet of sulfur. So we're going to have to take these electrons and bring them in here to form double bonds so that, oh no, that's not going to work for us. The electrons need to come from carbon to form double bonds here. Right? We can't bring double bonds in from here because carbon already has 8 electrons around it. So we're going to get this, which has 1, 2, 3, 4, 5, 6, 7, 8 electrons around sulfur. And then the other side, we're going to have to do the same thing. All right, so that shows us the carbon disulfide. Cn, we have 4 electrons brought by carbon, 5 here and 1 here, so that's 10 electrons altogether. Carbon, 1, 2 here, 3, 4, 5, 6, 7, 8, 9, 10. So nitrogen only has 4 electrons around it, so we're going to bring in some of these double bonds. Now it has 1, 2, 3, 4, 5, 6. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. We're going to have to bring in some more double bonds, more electrons to make a double bond. So there's carbon has 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen has 6, 7, 8. So that looks right. Where's the negative charge at? Because this whole thing has to have a net formal charge of -1 because it's an ion, right? So carbon brought 4 electrons, has 1, 2, 3, 4, 5. So that is a -1 charge. Nitrogen brought 5, has a 1, 2, 3, 4, 5. So there's a 0. So the negative charge is on the carbon atom. All right. Is there anything else we could do to help get the negative charge on the nitrogen? No, I think that's it. All right. So let's see. 992. Let's double check that one. Make sure we're not missing something. 992. Yep. 994. Draw Lewis structures for the following compounds. 994. ASH3, astatine hydride. ASH3. Astatine brings in 5, 6, 7, 8. So we're looking for 8 electrons altogether. There's 6, and then we have lone pair on astatine. ASH3. B, HClO2. Cl is the middle, HClO2. Again, this is a oxyacid. Now we have to remember, every time we're asked to draw the Lewis structure of an oxyacid, the proton is going to be coming off of an oxygen. So we have 2 oxygens coming out like this, and one of those oxygens has a hydrogen coming off it, right? Didn't we already draw this one? We're drawing a Lewis structure for HClO2, 994. Oh, I guess not. I thought we already drew this one. HClO2. All right, so chlorine brought 7 electrons. Oxygen brought 8 times 2, or 6 times 2 is 12. And hydrogen brought 1, right? So 12, 19, 20. So a total of 20 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Is that it? Oh no, 19, 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There we go, HClO2. Now the problem with this structure here, though, is that the formal charge here is 0. The formal charge here is 1, 2, 3, 4, 5, 6. Plus 1. The formal charge here is 1, 2, 3, 4, 5, 6, 7, minus 1. So we have to bring these electrons in so that that formal charges will be taken care of. Now the formal charge here is 0. It brought 6. It has 1, 2, 3, 4, 5, 6. Chlorine brought 7. 1, 2, 3, 4, 5, 6, 7. So that's the structure there. 990 for H2SeO3. H2SeO3. All right. All right. So again, we have selenate ion, right? And we have 2 protons coming off of this ion here. So again, this is an oxy acid with selenium in the middle, 3 oxygens on the outside, and then there's 2 spots in which the hydrogens are interacting. Okay, and this is going to have this kind of a structure here. Selenium has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. 9, 10, 11, 12, 13, 14, 15, 16. And that should be how many were brought. Let's make sure. Selenium brought 6. 6 times 3, 18, 19, 20, right? 6 times 4, 24, 25, 26. So there's 26 altogether. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Wait a second, what did I do? Was 26 right? 6 times 3 is 18. 6 times 4 is 24, 25, 26. Yeah, so there should be 26 electrons. Let's see. So, let's go back to this point right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 16 electrons left to... Hi. Alright, so we're in the middle of doing this problem here. 26 total electrons, right? 6 times 4 is 24 plus 2 from hydrogen, so that's 26. And now we have 10 gone, so we have 16 left. Well, selenium needs 2 more right there to get fill in octets. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 now. So that's 2 more, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Wait a second, start over. I lost count. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 16 left. 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. There we go. All right, so we can double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay. All right, now the only problem here is that this oxygen has a -1 charge. And the selenium here, which brought, how many did we say? Let's see, that was 5? Never know. Oh no, it brought 6 as well. Right? Yeah, it brought 6 as well. It has 1, 2, 3, 4, 5 electrons associated with it, so it has a plus charge there. So we want to move these 2 electrons in like that, and that will be our Lewis structure. All right, so now there's no formal charges. All right, we can double check that one. 994. Yeah. Okay. 994. That was H2SeO3. Now H3ASO4. 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 All right, so acetane has 5. So 5 from acetane. 6 times 4, 24 from the oxygens, and 3. So we have 24, 29, 30, 31, 32. 32 electrons altogether. Acetane, 4 oxygens, 1, 2, 3, 4. 3 hydrogens. Again, this is an oxy acid, so the hydrogens are coming off of oxygens, okay? And acetane has 8 electrons. So the question is, how many electrons do we have left? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 already being used up. So there's 28 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, this isn't 28, this is 18 left over, right? Yeah. So, let's see, is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, now we do the formal charges, and we see that acetane has a +1, oxygen has a -1 here. So we need to bring those electrons down there, and that will be our final structure. 994, oh, that's the last one in 994. 996, draw the Lewis structure for CH2O. Central atom is carbon. What is attached to 2 hydrogens, which is attached to 2 hydrogens and an oxygen? All right, so 996. We have a carbon as a central atom. 996, CH2O, like this, they said, right? We want to count the electrons. We had carbon brought 4, hydrogen, there's 2 of them, each one brought 1. Oxygen brings 6, 10, so there's 12 electrons altogether. 1, 2, 3, 4, 5, 6, 7, 8, fill that up first, 9, 10, 11, 12. Now we see that this carbon here, or this oxygen doesn't have everything it needs. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. But we're going to have to use these double electrons up here to fill up the octet of oxygen. So this is what the final structure is going to look like. There's no formal charges on there, and that's a chemical called acetone. Important chemical. All right, SOCl2. The central atom is sulfur, which is attached to an oxygen and 2 chlorine. SOCl2. Okay? SOCl2. SOCl, right? We want to make these evenly spaced. Chlorine brings 7. There's 2 of them. That's 14. Oxygen brings 6. Sulfur brings 6 also. So we have 14 plus 12. That's 26 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8 to fill up the octet of sulfur. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26. Okay? So this has a -1 formal charge. Sulfur here has a 1, 2, 3, 4, 5, a +1. So if we make this electrons into a double bond, then we'll have sulfur with a double bonded oxygen. And chlorine, 1, 2, 3, 4, 5, 6. Chlorines both have no formal charge. So that's our final chemical there. 998, assign formal charges to each of the atoms in the following structures. 998. Well, we see HOCl. So we have ClOOH. So this has a -1. We count how many electrons oxygen brought. 6. How many it has now? 1, 2, 3, 4, 5, 6, and 7 right around it. Chlorine brought 7, has 1, 2, 3, 4, 5, 6, so it has a +1. And this has a 0, and this has a 0. It brought 2 and has, no, it brought 1 and it has 1 right around it. All right, so those are the formal charges on that one. BSO3. Oxygen here has a -1. Oxygen here has a -1. Sulfur here has a +2, right? 1, 2, 3, 4, and it brought 6, +2. SO2, SO, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 2. So oxygen here has a 0. Oxygen here has a -1. Sulfur here brought 6, has 1, 2, 3, 4, 5, has a +1. All right. Those are the formal charges on those. 998. So again, you find formal charges by looking at 998, 9100. You're looking at how many electrons each of the element brought and how many it has directly around it. Lone pairs count as 1 electron for every, so there's 2 electrons in a lone pair, and then each bond only counts as 1 electron that's right around it. Okay, 9100. Draw the Lewis structure for HClO4 according to the procedure described in figure 912. Assign formal charges to each atom in the formula. Determine the preferred Lewis structure for this compound, HClO4. So we have chlorine in the middle, oxygen, 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 oxygen. This is again an oxyacid. This is what the thing is going to look like. All right, and then we identify the formal charges. Well, we should go back to this point. We have to identify how many electrons are brought. 6 times 4, 24, plus 1, or plus 8, right? 7 for the chlorine and 1 here, so 7 plus 1, 7 for the chlorine, 1 for the hydrogen. 24 plus 8 is 32. Chlorine has a full octet, so we need to 1, 2, 3, 4, 5. We have 10 electrons already used up, so we need 22 electrons to fill up somewhere. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22. Okay? These oxygens all have -1 charges, and chlorine has a +3 there. So we'll bring in 3 double bonds to satisfy everybody's formal charges. Now chlorine has 1, 2, 3, 4, 5, 6, 7, and that should be the Lewis structure there. 9102. Below are two structures for beryllium chloride. Give 2 reasons why the one on the left is the preferred structure. Well, the one on the left is the preferred structure because, let's see, 1102. BeCl, Cl. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So the formal charges here are 0 and 0. Beryllium is, let's see, so it brought 2 electrons to the table and it wants to have 2 electrons, so its formal charge there is 0 as well. So the other one here, beryllium with the double bond of chlorine. 1, 2, 3, 4, beryllium, going to another chlorine here, which is, all right, so here we have 6 electrons. So there's a couple of reasons why the first one up here has no formal charges. You see down here, 1, 2, 3, 4, 5, 6. This has a +1, and this one has a 1, 2, 3, 4, 5, 6, 7. That one's 0. But this beryllium here has a, brought 2, has 3, has a -1. So there's a +1 charge here and a -1 charge here. And also, beryllium is the kind of compound that group 2 atoms normally only have 2 bonds to them. All right, so because beryllium is a group 2 atom, it only wants to have 2 bonds to it. All right, 9104. How much time do we have left? 9104. Okay, use the Lewis structure to show that the hydronium ion can be considered to be formed by the creation of a coordinate covalent bond between H2O and water. So H2O, right, and a proton comes in, right? So the result is this thing. There, and this thing here has a net. So there's no charge here, no charge here, no charge here, but this has 1, 2, 3, 4, 5, 6, 7, 8, has 1, 2, 3, 4, 5. So it has a positive formal charge on it. So the net charge is a positive there, right? And so we see that when this bond is made, this element provides both electrons, or sorry, this oxygen here in this water, this element here provides both electrons to this hydrogen in the bond, and that's the definition of a formal charge, or a coordinate covalent bond, a bond in which one of the elements contributes both electrons to the bond. 9106, draw the resonance structure for CO3 2-, calculate the average bond order. CO3 2-. Okay, CO3 all right, so there's the Lewis dot structure, CO3, and this is going to have 2 negative signs on it, 2 negative formal charges on it. So there's our CO3 2- net formal charge, 2- charge. And draw, let's see, does it say to draw any resonance structures? Draw the resonance structures for CO3. Okay, so the resonance structures would all differ in that this double bond could be formed between those electrons there, or they could be formed between these electrons here. And in this case, this doesn't have the negative charge, those two have the negative charge. So this double bond can be in any one of these three places. The bond order here, bond order is basically a number associated with how many bonds there are. There's one bond here, so the bond order is 1. One bond here, the bond order is 1. One bond there, the bond order is 2. So if I take all the numbers of the bond order, one that has a bond order of 1, one that has a bond order of 1, one that has a bond order of 2, add it together 4, divide it by how many bonds there are, that's the average bond order, which is 4/3. So, or 1 and 1/3, right? So the average bond order there is 1 and 1/3. 9106, 4/3, yeah. Okay, so 9108 and then 9110, and then we're done. Okay? Oh, sorry, did I skip 9104? No, that was 9106. Sorry, 9108. All right, here we go. 9108. How should the NO bond lengths compare to the NO3 minus in the NO3 minus and NO2 minus? Whoops, that's not N. NO3 minus and NO2 minus. Okay, so those dot structures, you can work through those to make sure that you know how to do that sort of thing. How should the end bond lengths compare in the NO3 and NO2 minus ions? Which one of these, well, what's the average bond order here? 2, 2, and 1, that's 5 divided by 3, so 5/3 is the bond length here. Here it is 3 halves. So 5/3, that's 1 and 2/3, and this is 1 and 1/2, right? So this is the bond order. Sorry, this is the bond order. Therefore, this is a higher bond order. Therefore, this one should have a shorter bond. So the NO3 should have the shorter bond. And is that what they're asking? How the bond lengths compare? The NO3 minus should have a shorter bond. That's what we're predicting. And NO2 should be shorter than that in NO3 minus. Did I say that right? Let's see. This is 1.5. This is 1.66, right? 5, 3, 4, 5. So it's 1 and 2/3. 1 and 1/2. So let's look at that again. How should the NO bond lengths compare in the NO3 and NO2 minus ions? If I do this right, 2, 4, 5 divided by 3, and 3 divided by 2. 1.5, 1 and 2/3. So 1 and 2/3 is the shorter, the higher bond order, NO3 minus. 108. NO bond and NO2 minus should be shorter than the NO bond and NO3 minus. I'll have to take a look at that again. I don't think that's correct though in the back, because the higher bond order is the shorter bond, right? Higher bond order is the shorter bond. This is NO3 minus. This is NO2 minus. Yeah, I think that is correct, but I'll give you an update otherwise. So the NO3 minus should have the shorter bond as far as I understand. Because it has a higher average bond order. The Lewis structure for carbon dioxide was given, but 2 other resonance structures can also be drawn for it. What are they? On the basis of the formal charges, why are they not preferred structures? So we could have carbon like this, where we have a -1 and a +1, right? And that's not preferred. We could have the opposite, where we have carbon like this. Again, both of them are preferred because of the formal charges that are on the molecule. Those are not preferred structures because the Lewis structure diagrams, one oxygen bears a formal charge of +1, whereas the other one bears a charge of -1. Yeah. Okay. Good job.